Hello everyone, my name is Safa and we will be looking at Linxia Grand Theater in China as a case study of parametric modeling using Grasshopper. So the project is first analyzed through modeling of mass, wireframe, and skin. The modeling process started by extracting the curves that made the irregular shape of the dome. I defined 12 circles, each with different radius and height, and they are all parametric, which means they are changeable. I divided each circle into segments in order to extract the points. And then I used the battery list item to choose the points to create an arc that defined the specific pattern between each two circles as it shows here. And I repeated this process throughout all the circles. I then joined these curves and polar arrayed them along the circles to create the complete wireframe. And of course, each of these strips is modeled separately, but they're all parametric. So if I change one, the whole thing changes. I then piped them in order to get the skin. And for the mass, I extracted the circle's endpoints and created the section of the dome, then using the battery sweep 1 to generate the mass. So then the final mass is scaled down in order to allow for the skin to show, and this is a preview of it. That's the final parametric definition, in which I'll walk you through in a bit. Then coming to the second part, which is the physically based model, I chose 3 circles from my form to generate the physically based form. I divided the origin circle, which is the one in the ground, radially to create segments that can be referenced later as the second and third anchor points. I then extracted the naked points of the origin circle and made them as the first anchor of the simulation. Then I, again, using list item to choose the second radial grid. Then I joined its BREP and found the discontinuity along the curve. All of that is to extract the points that will be referenced to the second circle, which is this one here. And using curve closest points and then using them as the second anchors of the simulation. Of course, I defined the form's pressure, edge length, and load, and then entwined them together to flatten and combine them. And all of these are parametric and can be changed to alter the physically based form. And this is an example of how the form changed when I changed these 3 parameters. I have 3 options. And of course, I used a bouncy solver to simulate, to run the simulation. I also added a mesh pattern through Kangaroo's stripper because it was just fun, looked like a cake. That's the final definition, and I'll show it to you now. Okay, so since the definition is so dense, I'll just walk you through one strip of it. So I defined the circles, then moved them up in the Z direction. I divided them in order to get the points, and then using list item, I got specific points. I created an arc between them, joined it in order to polar array it along the circles. And basically the rest of the definition is the final skin pipe, the endpoints, and the arc section between them in order to create the mass. And so the algorithm is pretty simple of how to generate the form, but it gets repeated a lot, and in each strip, the list item is different. So at the end, it looks like this. And for the physically based simulation, I'll run it now. And if I change any of these parameters, the pressure, The edge length, it's pretty much cool. Kind of looks like a circus tent. And of course, if I change the original circles, it changes too, the height and the radius. And here, yeah, just explodes. And thank you for listening.